Today we have Dr. Aubrey de Grey of the LEV Foundation, who I'm sure many people know already, and we're going to talk about his RMR projects in a lot of detail. So let's get into it. And Aubrey, do you want to introduce yourself and your project?
Yes, thank you, Oliver. So my name is Dr. Aubrey de Grey. I am the President and Chief Science Officer of LEV Foundation, which is a public charity based in California, a 501c3 for those of you who pay tax in the US. And it is focused on research to bring aging under medical control. We focus on early stage research, so we don't do anything with human beings. We work entirely with mice. And our flagship research program is the attempt to find ways to make mice live a lot longer. The way we're doing it is by taking interventions that have already been shown by others to actually extend life in mice and putting them together, combining them to see whether we can get an additive effect. Now, there are plenty of good reasons to suppose that we could get an additive effect because many of these interventions are ones that are very different from each other. They attack different aspects of aging. And furthermore, we're interested especially in interventions that don't just slow aging down, but actually reverse it, that rejuvenate the mice. So for that reason, we are doing experiments that begin when the mice are already in middle age. What that means in actual numbers is we're talking about mice that normally live to about 2.5 years, and we start our experiments when the mice are already 1.5 years old. Now, for many, many years, there has been, in fact, probably half a century now, there has been a way to extend lifespan in mice or rats by about 4 months if you start at that kind of age. And that method is called calorie restriction. It just means you give the mice less food than they would like. More recently, in the past 15 years or so, people have discovered drugs that can effectively mimic calorie restriction. They can trick the mice into thinking they're in a famine when they're not. And these work more or less as well. So our goal is to beat that record of 4 months. We want to maybe get 8 or 12 months of life extension. And we believe that if we can do that, then this will be extraordinarily impactful in terms of public attitudes to the genuine possibility that aging can be brought under medical control.
Great. And you think a combination intervention is the solution to that?
We do. Partly that's on theoretical grounds that aging consists of the accumulation of a wide variety of different types of molecular and cellular damage in the body. And if you try to fix one or more of those types of damage, then you'll have some effect, but you really need to fix all of them, or at least most of them, in order to have a big effect. So we would expect some kind of additivity. The other reason why we now feel confident that this is true is because we've already done one experiment of this nature. We started it about 3 years ago, and it was pretty successful. We took 4 interventions at that point, which one was one of these drugs that I just mentioned that are what called calorie restriction mimetic. And that was really introduced as a kind of positive control, just to make sure that we were doing the experiment well, because we'd never done anything like this before. Other 3 were all some kind of damage repair, some kind of rejuvenation. And they were very different ones. One of them was giving the mice additional doses of telomerase. This is an enzyme that's very important for the cellular replicative lifespan, and mice don't make enough of it. They make some, more than we do actually, but they don't make enough of it to keep going. And it was shown maybe a decade ago that this is very beneficial if you give them more. So we did that. Second one was heterochronic bone marrow transplant. So that means we killed a lot of young mice and scraped the bone marrow and purified out the stem cells and injected them into the old mice in such a way that some of those stem cells would survive long term. And again, this has been shown by other groups to actually work, to actually extend life. And the third one was spinolytic. The idea was to remove senescent cells, which are, as many people will know, generally damaging. They accumulate during life and they seem to be actively toxic. So removing them is good. So we did all these things, and the result was confirmed our hypothesis. We did get an additive effect. We got more benefit. It was less clear in male mice than it was in female mice for reasons that we don't fully understand. But at least in female mice, it was a nice clean result. We got additivity. What we did not get, however, was any kind of record breaking. We did not exceed
Right.
this record that already exists. So that has led us to feel that the right next thing to do is to double down, so to speak. In other words, to do an experiment that's even bigger that involves not 3 damage repair interventions, but 8, eight some of which are not really damage repair, they're more slowing of damage, but that's okay. Um, but we feel we have a pretty damn good chance with this experiment of actually getting the result we want.
Okay. And just a note on that bone marrow transplant. How does that, for people that don't know, how does that work without getting rejected in this mouse study?
Right. So one useful feature of mice is that they have been bred in captivity in laboratories around the world for many, many years, literally more than a century. So what this has led to is that these mice are what's called inbred. That means that they're very, very closely related to each other and they will basically have the same genes. So that means that when you give cells from one mouse to another mouse of the same strain, you don't get any kind of rejection whatsoever. This is actually one reason why we have chosen not to go the route that some researchers have and deliberately avoid using these inbred strains. There's a
Mm.
strain HET3, HET3, which is a cross, a four-way cross. You take 4 different strains with obviously different genetic variations, and you cross them together, so you get a bunch of mice that are all genetically different from each other. If you use those, then there are some advantages. You get more of something that is known in genetics as hybrid vigor. Essentially, mice get, because they've got different versions of different genes, they have more of a chance of avoiding any kind of deficiency of one type of gene. But the downside is that you do get this rejection that you just mentioned.
Yeah,
Um,
hard to
and
study.
yeah, and as such, it means basically if we were to use that strain of mice, those outbreak strains, then we would either just have to not do cell therapies at all, or we'd have to use some kind of immune suppression, and we don't want to do that.
Yeah, and it doesn't, because when you're doing it in humans anyway, we'll probably have a source of young cells which are not immune rejected. So it's not even an issue for clinical
I
validation.
wouldn't quite go that far. I think that immune rejection is something that always has to be thought about when we come to humans. And so, for example, right now there are various cell therapy clinical trials going on for Parkinson's disease. Some of those trials are allogeneic; you use cells from elsewhere, and that kind of seems to be good enough just about because the cells that you inject survive long enough in the brain to do the job. But a lot of people feel that they won't survive long enough long term. And so one of the trials that's going on, run by Aspen Neurosciences, is using autologous cells, cells that have been taken from the person you're going to eventually treat and have been de-differentiated back into a pluripotent state and then redifferentiated into dopaminergic precursors, which are the cells that need to be used for this kind of study.
Yeah, so there's ways around it, but it's still a big issue, of course. But it's definitely makes it way easier in the mouse studies to study cell therapies because of this genetic matching, uh, ease of use, so to say.
And I will say one more thing about that, since you're asking me to get slightly technical. The
Yes.
kind of strains, kind of mice that we really like to use are a two-way cross, not a four-way cross, the way Het3 is, but a two-way cross. Here, what you have is every mouse is heterozygous. They've got one chromosome from one strain and one chromosome from the other strain, of each homologous pair. So what you have there is you pretty much solve the hybrid vigor problem. You do have the mice having different copies of things that can kind of compensate for each other, but you don't have a rejection problem because every mouse still is
Still don't have it.
identical to each mouse.
Okay.
It's only when you
It's
go
similar
four.
enough.
That's right. It's only when you do an F2 cross, a four-way cross, that you get the
Mm.
problem I described. But unfortunately, nowhere, Jackson Lab, whatever, has any of these two-way cross mice in
Yeah.
sufficient numbers for our experiment. We need a lot of mice for our experiment, a couple of thousand.
Yep.
So if we were to go that route, we would basically have to breed our own. And we may do that in the future.
Yeah. Yeah. It's a big issue in the mouse lifespan space. The kind of lack of UMHET3, lack of two-way cross, even age
I will say
67.
this, though. I will say this, though. My personal feeling is that the arguments in favor of using a four-way cross like HET3 in order to get reliable results. I believe it's been rather overblown, to be honest.
I think so.
I don't think there's a single example where Black Six, the standard
Mm.
mouse strain that everybody uses for lifespan experiments and that we use, has
Yeah.
ever actually misled us. I don't think
Yeah.
that's the case. So, maybe we shouldn't worry.
Yeah, I think so. There's not clear. I haven't seen an example of an UMHET3 discordant with another with a C57.
Well, yes. In particular, what we're interested in is being discordant in the misleading direction. In other words, something working in Black Six and then not working in Het 3.
Yep, exactly. So so that's kind of like the introduction, I guess we talked about that. Let's zoom out a bit and because I'm thinking of starting a project in this area as well, because I think there should be loads of people doing what you're doing. And a question I get about about this concept in general is why hasn't anyone done it before when it's so obvious?
It's so painful. Yeah, I mean, when I talk to my colleagues about this, to the other people in the expert community, everyone is really supportive. They say, "Yeah, it's fantastic that you're doing this." So there's enormous consensus that these
Yeah.
experiments are valuable and extremely valuable. But as you say, nobody's doing them. Why? Well, there are a few reasons. One reason is that they are genuinely very, very difficult experiments to do. The more interventions you throw into an experiment, the more
Right.
ways there are for things to go wrong and for you to end up with a result that doesn't really tell you anything. We're very live to that problem. And that's why we need so many mice, because what we do is a lot of different treatment groups with, just a single treatment to make sure we're getting it right with, for example, all but one of the treatments, so as to be able to identify antagonistic interactions where different interventions are cancelling each other out,
Mm.
and also, for that matter, to make sure that we have multiple different shots on goal in case, for whatever reason, something isn't working. So they're very difficult to do. That's one reason. The second
Mm.
reason, however, is that in academia, the way you get ahead, the way you get your next grant application funded, the way you get your promotion or whatever, is by publishing in top journals. And top journals, it's an enormous tyranny. Top journals just have their own preferences for what they like to publish. People constantly complain that top journals will never publish negative results when something fails to work. And
Mm.
that's no, it's appalling. Even the intervention assessing program that you just had three that I was mentioning earlier, you know, when they publish negative results, they publish them in niche journals. It's painful.
Mm.
Worse than that, what journals want to publish are tests of mechanistic hypotheses. They want people to see, that progress is being made in science as opposed to progress in medicine, which is what I'm interested in, right? And so, yeah, academics are just not incentivized. In fact, they're de-incentivized to do experiments like this. And then in the private sector, you've got a different problem, but it's just as strong. Namely, anyone in the private sector, they want to make money. And that means they want to leverage technologies that they own the intellectual property on, that they have
Right.
patented or whatever. And what we're doing is we're taking things from multiple different sources. Many of them are not patentable at all, or they're off patent. The ones that are patented are owned by different people. So again, there's not really any new intellectual property that gets created from an experiment like this. So again,
Yep.
there's no incentive. It's tragic. It's ridiculous. Yeah, that's the basic. Yeah, lots of reasons, but here we are.
Yeah, so difficulty in grant strategy, lack of grant funding for this type of work, I guess would be a fourth issue. Because if there was a dedicated grant for this, then it kind of solve that problem. Yeah, lack of patentability when you're testing stuff that is harder or not patentable, um, which wouldn't be an issue if you were testing things which were novel or patentable in some way. But that's like that's a completely different strategy. Yeah, so quite a few issues. And yeah, you found so your solution is what you're saying is like angel funders or donors,
Yeah, that's
essentially.
right. Philanthropy. I've basically had this problem throughout my career, and I've had this problem on purpose. I have deliberately gone after
That's
things
true.
that are being neglected, and typically the reasons they're being neglected are not because scientists are dumb or not understanding that the things are important, but rather
Right.
because the funding sources are not aligned for it. So yes, I've been able for the past 20 years to attract occasional people who are willing to write big checks to basically just have faith that I know what's important to do. And that has worked out pretty well over the years. And of course, small donors are also really important, and we try to build that up. But we are very much still in the position where the bulk of our funding comes from large donations from a small number of people. And of course, that's very sporadic, and it's very frustrating having to, keep grinding away, begging such people to let me do this work.
Yep. So one issue there is cost. What um so someone uh someone mentioned to me recently they liked the idea, but they wanted to try and bring the cost per mouse down to like as cheap as possible levels using like AI labs and cheap to operate jurisdictions like Brazil, India, China, for example. Is that realistic or is it not?
So we are constantly looking for ways to reduce the cost, but of course you can take that too far. I mean, ultimately our goal is to maximize the impact per dollar, right? And impact means the likelihood that the experiment works. It means the likelihood that the experiment will be believed to have worked. We don't want to get into a position where people think that our results are unreliable. So yeah, there's all manner of different considerations. But yes, we're constantly talking to people all over the world in an effort to bring the costs down, and it works to some extent. So, for example, we're currently planning to do our next study in Spain at a facility that is going to be quite a bit cheaper than the place where we did the first experiment. We're forming good relations with various of the suppliers of the reagents that we need. So we're getting several of those reagents for free. So we're doing everything we can to bring the cost down. Uh, Um, um, Another thing we're doing is we are being creative about staggering the study.
Mm.
As I said, there were lots of treatment groups. In the first study, there were, well, depending on how you count it, there were, I guess, really 38 treatment groups. And this time there's going to be probably twice that. But we don't have to do them all at the same time. One option that we are definitely not favoring at this point is to do only one sex. So that means only half as many mice. But we feel that is really at risk of giving a larger chance of failure. So I mentioned that in our first experiment, the male mice, the results were a lot more messy, shall we say. It was harder to really claim that we got this additivity that we needed, where we did get it with the female mice. So we really don't want to take that risk. However, there are other things we can do. For example, the treatment groups that get all but one of the interventions are the main value there is to identify antagonistic interactions where things cancel each other out. But we don't expect that to be a very common event. So we
Yeah.
could, for example, do those treatment groups with fewer mice than before, or
Right.
we could just do them later. We do feel that we need to do the single intervention treatment groups at the beginning because we want to be sure that we are doing the study correctly. Um, and of course, the main thing we want to do is the real McCoy. We're giving the mice absolutely everything. We want to do that at the beginning. But there are various ways in which we can stagger the study so that we could get going with only a couple of $1 million rather than with the full blown $6 or $7 million that we need for the whole thing.
Right. Yes, there's three types of groups other than the control group. There's the monotherapy, the leave one out of all combinations, and then all all therapies.
That's right. And there are subgroups within that. So, of course, first of all, there's everything you just said in males and also in females. Secondly, there is the question of how you do the controls. So, in the first study, RMR1, we had two types of controls for each intervention, a mock and naive. So, the naive control would be you just don't give them the thing.
Mm.
But mark is you give them an inactivated version of the thing. So basically, the idea is to be able to check whether the method of delivery of the intervention is having an effect. And we're going to want to do something like that this time as well. Another thing we want to do this time that's different is the way in which we're using rapamycin, which was one of our four interventions last time. But as
Yep.
I say, it's really a positive control. We are making it more, if you like, more explicitly a positive control this time around.
Yeah.
So yeah. And then there are a few other things that we're doing differently. We're going to give the mice running wheels, which they didn't have last time, and which tends to be good for mouse span. One thing that's very important is we're using smart cages. There's a wonderful company named Olden Labs that have
Mm.
created these cages that record enormous amounts of data automatically,
Mm.
and so it saves a lot of manpower, and so it
Yep.
saves money.
Yep.
But also you just get more data. You just get, things that you couldn't measure with technicians.
Yeah, for sure. So yeah, a lot of different groups and the running wheels. Yeah, that's a good point. Out of all the mouse lifespan studies done currently in old age starts, how many are using running wheels? Do you know? I don't know.
A lot of studies do, and a lot of studies don't. Realistically, we probably should have used running wheels last time. We kind of knew that they were good, and we didn't really have. But budget reasons were,
Mm.
a problem last time around as well. For example, with the heterochronic bone marrow transplant that we did,
So,
we were not able to do to replicate the protocol that was published and that was successful in other people's hands
mm.
because of cost. It just needs a lot of stem cells. Um, so we were quite pleased that we did get some benefit from the HSCs because the amount that we put in was and the amount of engraftment that we got was considerably less than what was published in the prior work. Yeah, I mean, yeah, cost is always an issue.
So running wheels are good, um, if you can afford them, and they're providing. Is it like more? It's normalizing that aspect of exercise in a way because it's
Yeah,
and you can see whether they're running. I guess it's like an additional frailty index marker in a way as well. Because if they're going to be running more, so it's like a surrogate marker for health span and frailty. So it sounds like a good idea. Yeah, on the subject of rapamycin, so there's longevity dosing protocols, once a week, because of the longer half-life in humans of around 60 hours, although it's very variable, and the Cmax is very variable as well. So it's quite hard to study in humans without doing area under the curve for rapper exposure, which none of these studies are done, unfortunately, it seems. And there are also issues with formulation and gastroprotection issues as well. So those things may be why these studies failed, but yeah, there have been two, I think, RCTs, randomized controlled trials, where the first one didn't meet the visceral fat endpoint, which I'm not really surprised. I'm not sure why that was an endpoint as a primary outcome. And then the second one was just recently showing a reduction in get up and go kind of exercise capacity on a 6 milligram weekly dosing. Same again, like the caveats of I don't know about the encapsulation and I don't know about well, I think, and then no one studied the area under the curve because you want to get that washout to a very low level, well below 1 nanogram per mil blood level because 5 milligrams is the cutoff for immune suppression, and then mTOR1, mTOR2, etc., etc. Do you have any tips on how to validate benefits in humans in the way that we see so consistently in mice?
yeah. Well, first of all, I do not think that rapamycin or any other calorie restriction mimetic will be particularly useful in humans or in any long-lived species. That's because, first of all, on theoretical grounds, from an evolutionary perspective, one just expects that calorie restriction will work less well in long-lived species simply because in the
Yeah.
wild, long famines are less common than short famines. And so there's less selective pressure to be able to optimize for them. But also, we see it. People have done, calorie restriction experiments, the actual calorie restriction and mimetics, and also genetic models, similar things. And it's very clear, in species that live a few weeks, like nematode worms, you can multiply the lifespan by like 5 or 10. In mice, you can get like, 50% increase if you start early in life. In dogs, Purina did a CR experiment 30 years or so ago with Labradors that live maybe 11 on average, and they got about 10%. Um, of course, there were these two enormous monkey studies, which got a couple of percent if you're lucky. One of them kind of didn't work at all. So we know that this is not going to work. And we certainly know that cleomimetics are never going to do more than what calorie restriction itself does because it's activating the same pathways. So I'm not really interested in that. We're using it in mice as a positive control because it worked well in mice, but that's a different question. So then, in terms of um, what to look for in actual clinical trials of other things that might be more beneficial. Well, I mean, of course, there is this thing now going on called the HealthSpan X Prize, which I largely designed. Like I was involved in, I essentially led the early stages of the design, and it's very much a rejuvenation prize. It's got my fingerprints all over it. But yeah, I mean, we are the scientific advisory board, which of course I'm on, is very cognizant of the problems of ensuring that you actually achieve something. So the headline goal that allows you to win the prize is that you need to rejuvenate people's age by at least 10 years. You get more if you do 20 years. And you need to do it with an intervention that is performed for a maximum of 1 year. So that's proper rejuvenation. But how we measure biological age at the beginning and the end is not with any of these, for example, epigenetic clocks or any of the more modern approaches, because we just don't feel that those things are reliable enough. It's all on the basis of function. So there's immune function, there's muscle function, and there's cognitive function. And for each of those things, we have three different measures that are that, that are required for the competitors to use.
Yeah, so it's a tricky one. The CR and the wrapper and all the smaller effect size stuff like metformin and blood pressure drugs and so on in the mouse lifespan studies. So going back to the positive control, so is this a kind of disconnect between mouse and human biology? In the case of rapamycin, more rapamycin than Crohn, CR specifically.
I don't really think so, no. I think it's just, it's all about lifespan. The longer you live, the less impact calorie restriction or any kind of calorie restriction mimetic is going to have.
Related counts. Right, right, right. So the damage removal, so to say, is more important in longer lifespan, potentially.
Definitely.
So there may be the opposite discordance between effect size and damage removal in shorter lived species like mice.
Yes, but of course, since we're starting late in life, anything that slows down the accumulation of damage, which is what calorie restriction does and CR mimetics, is going to have a smaller effect than if you start early in life. So, in particular, you can get maybe 4 months of life extension in mice by calorie restriction started at middle age, where you can get best part of a year if you start weaning and you do it for the entire rest of their life. So yeah, and I'm rather interested in people who have the misfortune to be already alive and to have accumulated a fair amount of damage already. So that's another reason why I'm much more interested in bona fide rejuvenation in turning the clock back rather than just slowing the clock down.
So okay, so in terms of thinking about therapies, there may be these ones which are how would you classify CR and rapamycin and those kind of similar therapies?
Well, I mean, there are ways to slow damage down. So calorie
Right.
restriction causes life extension by activating a wide variety of pathways that are involved in preempting damage, stopping damage from being created in the first place, and doing so at the expense of things that are more beneficial in an ad lib context. So, in particular, if you're in the wild and there's plenty of food, then the optimum strategy is to grow as fast as possible so as to have offspring before you get eaten. Whereas in the famine, having offspring is a bit of a waste of effort because the offspring are going to die of starvation before they have their own offspring. So it makes more sense to hunker down and try to outlive the famine. Of course, there's an enormous amount that we still don't understand about the mechanics at the molecular level of how calorie restriction works.
Yep.
But we don't really need to. We just know that it does work and we know why.
Mm.
We also know why, for that same reason, it does not work particularly well in long-lived species. So then the same kind of thing is true for rejuvenation. We don't really need to know the fine details of why this or that intervention works, what it repairs. We'll always have working hypotheses for any particular intervention for what it's targeting. Senolytics are, there to remove these things called senescent cells, which everybody knows are bad for you. But in general, we can infer from the results that are seen in lifespan experiments in life that these interventions also have additional benefits that are not kind of to be expected per se. It's actually knock-on effects on other types of damage. So this can really, in the early stages of study of getting rid of senescent cells, when people made genetic models where you could get rid of cells quickly and easily. But the benefits of the mice that were given these things were much broader than anyone really expected them to be. So this was a kind of, wake-up call saying that if you like, the crosstalk between different types of damage accumulation is rather significant than I would have certainly guessed it would be.
Mm.
And yeah, I mean, basically, if you get a significant life extension starting late in life, from just one intervention, then you know that there's got to be a lot of knock-on effects to basically, to impact pretty much everything that is life-limiting. And this is why it's plausible that we will get this additive effect. When you hit more things, you're gonna, have greater impact in these direct way than well.
Right. So there's two main categories. There's the damage removal ones, and then the or replacement. I guess it's the same kind of category because if you're doing stem cells, you're replacing rather than removing. So there's the damage removal or replacement, and then there's the slowing strategy. And possibly it's going to be the effects of the slowing strategies are going to be exaggerated in mice versus humans, and potentially the opposite in damage removal, even in mice, even if they started in later age compared to humans.
Yeah, well, so I would say that damage retardation, like calorie restriction,
Yeah.
is a special case in that it has evolved to exist at all as a life extension strategy, but
Mm.
the pressures that have caused it to evolve have this rather unfortunate feature that we end up with a weaker response in humans. But one can certainly imagine other damage retardation interventions that are equally effective, whatever the length of life of the species. So one of the interventions we're planning to use in the next study is deuterated fatty acids.
I was about to bring it up. Yeah.
Essentially what we have here is a way to slow down the accumulation of oxidative damage. And it is a retardation thing. It doesn't remove pre-existing oxidative damage, but it certainly seems to work. And we believe it would work just as well in humans as it would in mice. Saying that, though, it does not solve the problem of starting late in life. If you want to help people who are already in middle age, or indeed mice that are already middle age, then slowing down the further accumulation of damage will have less of an effect. Whereas damage repair will have more of an effect in late life than it will early in life, again, irrespective of the species.
Yeah, there's actually some interesting human data already for deuterated fatty acids in there's a bunch of case reports from the main Misha's company trying to commercialize it. Very expensive, unfortunately, at the moment
But
to manufacture.
getting less expensive.
Hopefully.
There was a huge breakthrough about 5 years ago. So initially, the only way that this stuff could be made was by total synthesis. Very laborious chemical procedure. Yeah. And then a group in, if I remember rightly, Australia, but they have an outpost in Serbia or somewhere like that. They figured out a fantastic catalytic process that
Mm,
means they can now make grams of this stuff for pennies. It's like
okay.
really, really fast, very efficient. It deuterates the exact correct
Yep.
hydrogen atoms. It does not work on linoleic acid. You have to
Uh,
have 3 double
okay.
bonds rather than 2.
Yeah.
Honestly, that's fine. Arachidonic acid is the one that's mainly being used, and also
Yep.
DHA, and this is really, really good. So, yes, the cost is definitely not prohibitive anymore.
Okay. Yeah, that's an interesting one. And are you planning on doing omega-6 and omega-3 or EPA and DHA and AA?
At this point, we're just gonna use arachidonic. That's the one where most of the work has so far been done.
Yeah, yeah, yeah. Yeah, it's actually surprising. It's quite like just weight-wise, it's very I think it's the biggest contributor to uh PUFA lipid peroxidation in the body. So yeah, there are these okay, so there's two main categories and then there's like some exceptions with Quran and probably other things as well. So how are you choosing these eight to as the priority? And
Yeah.
out of taking into account like all of the mouse lifespan studies that have been done so far, including ones which are transgenic or started before birth.
Yeah. So the number one criterion that we use is that somebody else has published successful life extension, ideally starting late in life. And, that's a pretty difficult, that's a pretty high bar. Not many people have done such studies. So that if we had been doing this new experiment 3 years ago when we did the first one, we would not have had the option to do 8 interventions. There just weren't enough things that had good enough positive data. But during the course of the first experiment, real stream of studies came out showing exactly that this could be done. So that's one criterion. It's not absolute hard and fast. We don't require that would be happening, but that is certainly heavily weighted, as you say. Another criterion, which is of course very important, is that the interventions should be as different as possible from each other, because we don't want to duplicate things. Beyond that, really, the other considerations are things like cost, just practicality in terms of doing these things to these mice. We want to do every kind of intervention, cell therapies, gene therapies, and so on, which is something that is not done in the intervention testing program, or indeed in pretty much any of the other programs that are looking at this kind of thing.
Mm.
They stick to things that can be supplied in the food, whereas we are
I know
happy to
it's annoying.
inject our mice. But yeah, so basically we just want to maximize the chance that we'll see an additive effect, and ideally a really big additive effect. Our goal is to treble the effect size that calorie restriction can achieve, which, as I mentioned, is about 4 months. We want to get to 12 months.
Yep. So 12 months started in old age and reproducible, I guess, as well. How does that compare to the recent? I think we're emailing about it actually. The recent telomere rivers peer review
So,
pending study
yeah, I really
with
don't
chip.
want to comment on that paper because, as
It's
of
too early.
now, it doesn't have much credibility. The lifespan curves that were shown in the preprint of that paper that the authors put online, well, they've got problems. They don't make sense. I and several other people have written to the senior author asking for clarification of this, asking for the raw data, and so on, and he has declined to make anything available until the paper is accepted for publication, which is definitely within his rights to take that view, no question. But given that the questions arising from the preprint are really quite severe,
Yeah,
there is,
the
of course, the
the
concern
duplication.
that the thing never actually will be published because people will simply have too much difficulty with this.
Mm.
But, I remain hopeful. We will see. And if it does get through peer review, and if the senior author does then make the raw data available, then, I think there will be definite, um, you know, justification for other people trying to replicate the study and see if they
Mm.
get the same results. But the result that is shown is just really, really big. The
Yeah.
life that is shown is just so big that it's very hard
Believe.
to take it at face value.
Yeah, yeah. And there were some issues in the control group as well, early deaths, which I saw.
Yeah. Yeah.
Yeah, so it's a tricky selection process for choosing which combinations to do because they have to be, peer reviewed and also old age starts and ideally.
We're not we're not too worried about peer review. So, for example, one of the interventions in the upcoming study is a senolytic, same as we did last time. It's a
Mm.
different one, and it's had a lifespan study done, but that study has not yet been published.
Mm.
So, we're going with that one simply because we've seen the data and we believe that it works, and we believe that it's a very promising approach, very different mechanism from other senolytics. So, we've just made a judgment call that this is the right thing to go for.
Mm.
But in general, yes, and I think out of our 8 interventions that we're going to use, only 2 of them are unpublished. The other one is depoofers. There have been lifespan experiments there as well that in mice
Yeah,
that have not published yet, but that
yeah,
look good.
yeah, yeah. Agreed, agreed. So, is it ever tempting to do a Hail Mary and do 100 therapies all at once, 50 therapies, something much higher number, high risk, high reward concept?
Yeah, I mean, at this point, probably not. At this point, I think 8 is the right kind of number to be going for because there's no way to describe how challenging these experiments are. So
Mm.
many things that can just completely go wrong and invalidate the thing where you didn't get the result you wanted.
Mm.
You didn't do the experiment in a manner that was informative
Mm.
with the best possible efforts. Even monotherapy experiments often go wrong,
Oh yeah.
as anybody that has ever done lab work well knows. So yeah, we're really pushing the boundary already of what's practical in an actual lifespan experiment.
So in clinical medicine and a little bit in preclinical as well, but especially in clinical, I think because it's even more expensive, very very expensive, and lots of money and legal lives on the line as well. There's the Equator Network, which you might not have heard of. Have you heard of it? It's clinical, so it's probably most preclinical scientists are not familiar with it. But it's essentially every type of clinical study you can have there's an international consensus checklist on how it should be performed and written up as well. So it's kind of like stuff before, for it needs to be registered in this certain database and it needs to have this kind of prior outcomes submitted, so you can't change them later on and p-hack your way around. And then so there's the before stuff and then the after stuff of how it should be published and what data should be shown in what format. And it's really good. I think it's really good. Really transformed like the quality of randomized controlled trials, meta-analyses, whatever, anything you can imagine. But I'm wondering if maybe you should make a similar thing for mouse lifespan studies, because that definitely doesn't
Yeah,
exist.
yes, that would be good. Certainly, a lot of studies have deficiencies that are a problem. So here's an example. So just a month or so ago, the intervention testing program published a bunch of negative results. One of them was with alpha-ketoglycerate, which had positive results in other people's hands. But what the ICP did was they measured the blood concentration of AKG in the mice, and they found that it was only 1/6 of the target concentration, that for whatever reason, that had not really worked. Now, that's bad. It means that they didn't really do the experiments that they wanted to, and they didn't draw enough attention to this. It was just in a table somewhere. They didn't mention it in the text, and I berated them for that. But the point is, at least they measured it. Most
Right.
studies don't even measure the concentrations of things, they
Yeah.
just hit and hope. So, yeah, that's an example where you're absolutely right. However, I will say that for the experiments that we're doing, that's not really the main problem. The main problem is just doing the experiment correctly at all, because it's so
Gotcha.
challenging with so many different interventions.
Right. Right. Aubrey had to jump at this point, so we ended it there. But a very interesting discussion, and I'd like to see more projects in this space, as well as this lifespan study design checklist and reporting checklist. So both, like that example Aubrey was giving, it's required to measure certain types of blood or tissue levels, blood serum, plasma, whole blood, etc., or intra-organ levels of your active compound or as relevant in the design at the beginning. And then in the reporting criteria, it's required to report them in an easy to view way rather than hidden in supplementary data or table descriptions, etc.